Have you ever just stopped to think about how you're actually seeing this right now? It's so easy to take for granted, right? But every single color, shape, and tiny movement you experience is being captured and processed by this incredibly small biological marvel. We're talking about a tiny sphere, on average just 2.3 centimeters across, that somehow manages to take in all the light bouncing around the universe and instantly translate it into the reality you perceive. It is absolutely mind-blowing when you really stop to think about it.
Welcome to This Explainer. I am so thrilled to have you here today because we are going on a seriously fascinating journey. Our goal, we are going to completely demystify two incredible things: the brilliant biological machinery of your own vision and the breathtaking physics happening right above your head in the sky. By the time we wrap up, I promise you, you'll never look at a rainbow, a sunset, or even your own eyes in the same way again.
Okay, let's dive right into this. Here is our path for today. First, inside the human eye. Then, fixing defects of vision. Third, prisms and rainbows. Fourth, atmospheric refraction. And finally, the scattering of light.
Let's kick things off with Section 1, Inside the Human Eye, the Biology of Vision. You can really think of your eye like an incredibly advanced organic camera. First up, light passes through the cornea. That's a clear, protective window at the front, and it's where most of the bending or refraction of light actually happens. Next, it moves through the pupil, which is essentially the camera's aperture. The dark, muscular iris controls the pupil's size, opening it wide when you're in a dark room and shrinking it down in bright sunlight. Then the light hits the lens. This is a jelly-like protein structure that fine-tunes the focus, projecting a real, inverted image onto the retina at the very back of the eye. Think of the retina as your light-sensitive film. It's totally packed with rods and cones that convert that light into electrical signals. Finally, these signals race down the optic nerve straight to the brain, which flips the image right side up and tells you exactly what you're looking at.
Now, what's truly wild about this lens system is something called the power of accommodation. Your eye's lens isn't just a rigid piece of glass. It's flexible, and it's held in place by these things called ciliary muscles. When you look at something way off in the distance, like a mountain, those ciliary muscles relax. This pulls on the suspensory ligaments, flattening the lens out and increasing its focal length. But when you shift to look at something super close, like your phone screen, those ciliary muscles contract. That takes the tension off the ligaments, allowing the lens to bulge and get thicker, which shortens the focal length. It is literally an instant, automatic autofocus system built right into your head.
But even this biological autofocus has its limits. For a young adult with normal vision, the least distance of distinct vision is exactly 25 centimeters. That's the closest you can hold an object to your face and still see it perfectly clearly without straining. If you try holding a book any closer than 25 centimeters, those ciliary muscles simply can't bulge the lens any further. The image blurs, and if you keep forcing it, you're going to end up with a pretty nasty headache from the muscle strain. So what happens when that incredible focusing system isn't perfectly calibrated?
That brings us to Section 2, Fixing Defects of Vision, when the lens needs help.
The crucial thing to understand here is where the light actually lands inside the eye. Let's talk about myopia first, commonly known as short-sightedness. In this case, the eyeball might just be a bit too long, or the lens is too curved. This causes distant objects to focus entirely in front of the retina, rather than directly on it. How do we fix it? We use a diverging, concave lens. This spreads the light rays out just enough before they even enter the eye, so they land perfectly on the retina. On the flip side, we have hypermetropia, or farsightedness. This is the exact opposite. The eyeball is too short, or the lens is too flat, meaning nearby objects focus behind the retina. We correct this one with a converging, convex lens. It pre-bends the light inward to pull that focal point forward, right onto that retinal screen where it belongs.
Beyond just the shape of the eyeball, we also have to deal with the simple passage of time. As we age, two major things can happen. First up is presbyopia. Remember those dynamic ciliary muscles we just talked about? Well, over time, they weaken and the lens itself hardens. This means the eye loses its power of accommodation, specifically struggling to bulge enough to see things up close. The crazy thing is, even someone with myopia can develop presbyopia as they age, which is exactly why people often end up needing bifocals. The second issue is cataracts. This happens when the normally crystal clear lens becomes cloudy or milky because the proteins degrade over time. It's kind of like trying to look through a foggy, frosted window. Fortunately, modern medicine is amazing and can completely fix this by surgically removing that cloudy lens and dropping a brand new artificial one right in its place.
So now that we know how our eyes capture light, and how we fix them when they don't quite get it right, it's time to ask a much bigger question. The rods and cones in our retinas detect light and color,
But where do all those colors in the world actually come from in the first place?
Let's explore that in Section 3, Prisms and Rainbows, the Spectrum of Light. Sir Isaac Newton actually figured this out famously using just a simple glass prism. When pure white sunlight hits a denser medium like glass at an angle, it slows down and bends. This process is called refraction. But here's the secret. White light is actually a chaotic mashup of every single color in the visible spectrum. And because each color has a completely different wavelength, they all slow down and bend at slightly different angles. Red light has a longer wavelength, so it kind of just powers through and bends the least. Violet light, on the other hand, has a very short wavelength, so it gets slowed down and bends the most. This varying degree of bending physically splits the white light into that magnificent, distinct band of colors we call spectrum. In physics, we call this dispersion.
The amazing thing is, nature performs this exact same prism experiment all the time, just on a massive scale. When sunlight hits a tiny, spherical raindrop suspended in the air, three specific things happen in sequence. First, the light undergoes refraction as it enters the droplet, immediately dispersing into its constituent colors. Second, those separated colors hit the back wall of the raindrop and undergo what's called total internal reflection, bouncing right back toward the front. And third, the light undergoes refraction one more time as it exits the droplet back into the air, bending even further and widening that spectrum. When millions of tiny raindrops do this all at the exact same time, you get a rainbow.
And here is a highly practical, genuinely fascinating takeaway from this explainer for you. You will absolutely never see a rainbow while looking toward the sun. Because the light has to enter the raindrop, reflect off the back, and bounce right back to your eyes. The geometry demands that the light source must be behind you. So if a rainstorm just passed and the sun is peeking out, always put your back to the sun if you want to spot the rainbow.
All right, so we've conquered rainbows, but let's look up a little higher, past the rain clouds, straight into the night sky. Have you ever wondered why, when you look up at night, the stars are constantly twinkling and shimmering, but the planets just shine with a steady, solid light?
Let's find out in Section 4, Atmospheric Refraction, Bending Light in the Sky.
See, the space between us and the stars isn't empty. It is totally filled with Earth's atmosphere. And our atmosphere isn't just a static, uniform blanket. It's made up of layers of hot and cold air all swirling and shifting around with completely different optical densities. When the light from a star, which is so unbelievably far away that it looks like just a tiny single point of light, hits the shifting atmosphere, that single beam gets refracted, or bent, rapidly in different directions. To our eyes on the ground, the star's position seems to literally jump around slightly, and its brightness fluctuates, and that is twinkling. Planets, however, are much closer to Earth. Instead of being a single point of light, they act as what we call an extended source, essentially a collection of many point sources clustered together. So while individual beams of light from the planet still get bent by the atmosphere, those different shifts basically cancel each other out, giving us that steady, non-twinkling glow.
Atmospheric refraction is also responsible for one of the greatest optical illusions that you experience every single day. Because the Earth's atmosphere gradually bends the sun's light down toward the surface, we can actually see the sun over the horizon before it has physically risen. The apparent position we see is slightly higher than its actual physical position. This atmospheric bending gives us about 2 extra minutes of visible sunlight before the actual sunrise, and another 2 extra minutes of visible sunlight after the actual sunset. How cool is that?
Which brings us to our final stop, Section 5, the scattering of light, painting the atmosphere.
To really understand the colors of the sky, we first need to understand something called the Tyndall effect. When light passes through a completely pure vacuum or a true liquid solution, it's totally invisible. But if the medium is filled with tiny particles, like dust, smoke, or water droplets, those particles act like tiny obstacles. The light rays hit them and scatter in every direction. This scattered light is exactly what makes the actual path of the beam visible to us. You see this all the time when sunlight streams through a dense, foggy forest canopy, or when a bright movie projector beam cuts through a dusty, dark theater.
Which leads us perfectly to the ultimate childhood question. If sunlight is white and contains all the colors of the rainbow, why on earth do we look up and see a blue sky?
The answer all comes down to the size of the particles and the distance the light has to travel. High up in our atmosphere, the air molecules and fine particles are incredibly small. We're talking smaller than the wavelength of visible light. These tiny particles are highly effective at scattering shorter wavelengths, like blue light, but they mostly just let longer wavelengths, like red light, pass right on through. So, during the day when the sun is right overhead, blue light gets scattered in every possible direction across the sky, and that's what enters our eyes. But at sunrise or sunset, the sun is super low near the horizon.
That light has to travel through a much thicker slice of the atmosphere to reach you. By the time that light finally gets to your eyes, almost all the blue light has been completely scattered away, leaving only the longer red and orange wavelengths behind to paint those gorgeous sunsets.
To really drive this point home, just think about the astronauts on the International Space Station or walking on the moon. Even though the sun is blazing brightly out there, the sky around them isn't blue or white or red. It is pitch, absolute black. Why? Because there's no atmosphere. Without an atmosphere, there are no particles to scatter the sunlight. The light just travels straight in a perfect line. Unless you look directly at the sun itself or an illuminated object, the surrounding space remains a totally dark void. It really proves that the beautiful blue sky we enjoy every day is entirely a product of our atmosphere just playing with the spectrum of light.
Which brings us to our final, lingering thought for this explainer. From those microscopic ciliary muscles focusing your tiny 2.3 centimeter eye, all the way to the massive atmospheric layers bending starlight and scattering a blue sky. It really makes you wonder, doesn't it? How much of what we see is the objective world, and how much is just light playing complex, beautiful tricks on our biology? The next time you see a rainbow or watch a sunset, I hope you remember the incredible science that makes that moment possible. Thanks so much for joining me on this explainer, and keep your eyes open to the wonders around you.